I want you, the listener, to just imagine for a second that you're stepping into this massive, echoing lecture hall at a major university.
Right, like a really old school traditional physics department.
Exactly. And the air is just thick with anticipation. The room is absolutely packed with the world's most brilliant and, let's be honest, probably the most skeptical theoretical physicists alive today.
Oh, without a doubt, they're a tough crowd.
Right. And for over a century, these minds have operated under this towering shadow of Albert Einstein. I mean, they've built their entire careers, their textbooks, everything on general relativity.
It's the bedrock of modern astrophysics.
It is. But up on the blackboard at the front of this room is a radical new paper. It was published in May 2026 by a physicist named Sriman Barua. And look, if the math on that blackboard holds up, it challenges, well, it basically rewrites absolutely everything we thought we knew about the ultimate monsters of the universe.
Black holes.
Black holes, yeah.
It really is the kind of paper that forces a complete paradigm shift. We aren't just talking about a minor tweak to existing models here.
Right, not just a little footnote.
No, not at all. Or like a slight adjustment to a cosmological constant. Burroughs' work proposes a fundamental rewrite of the rules governing space-time, gravity, and the entire life cycle of the most extreme objects in existence.
And that is exactly what we are doing today. Our mission for this deep dive is to unpack the absolute boldest, most reality-bending claim within Burroughs' new model, which is called the absolute medium framework, or AM, right?
That's right, the AM framework.
So the core claim is just staggering to me. It's that supermassive black holes do not live forever.
Which is pure heresy in standard physics.
Total heresy. So we are going to trace the complete chronological life cycle of a black hole through this new lens, from the explosive death of a star to a frozen knot in the fabric of space, all the way to this invisible, dissolving strain field humming in the dark.
It's a wild journey.
It really is. And we have the source paper, we have the rigorous mathematical proofs, and we are going to look at the observational data that might just prove Einstein's model is incomplete.
So, to really do this justice, I'm going to step into the shoes of that late physicist standing at the blackboard.
Awesome.
My job today is to defend Barrow's findings, walk you through the actual mechanics of the absolute medium, and, explain why the math forces us to abandon the idea of eternal black holes.
And I am going to be the voice of that deeply skeptical audience. I'll be pushing back, asking for the physical reality behind the equations, and demanding the smoking gun evidence.
Bring it on.
Because standard physics tells us that black holes are basically these bottomless pits that trap everything, including light, until the end of time. If you're going to stand there and tell me that a billion solar mass titan just structurally fails and dissolves.
I know it sounds crazy.
It does. You have to bring irrefutable proof.
And I welcome the skepticism, really. The burden of proof in physics is always on the challenger, and the absolute medium framework has some very heavy lifting to do.
Okay, let's get right into the foundational conflict then. We need to redefine the board the game is played on, which is space-time itself.
Right.
Under standard general relativity, we are taught that space-time is essentially a geometric concept, right? It's an abstract grid.
Yes, the classic rubber sheet analogy.
Exactly. Mass tells that geometric grid how to curve, and the curvature of that grid tells mass how to move. When a really massive star dies, it collapses infinitely inward, creating a singularity.
A point of infinite density.
Right, and the geometric curve becomes a literal bottomless pit. But Barrou's AM framework throws out that geometric abstraction entirely, doesn't it?
It completely flips the script. The absolute medium framework argues that space-time is not just abstract geometry, it is a physical, elastic substrate.
Okay, wait, when you say physical elastic substrate, I need to visualize this. Are we talking about an actual material permeating the entire universe?
Think of it as a continuous cosmic medium. Yeah. It has real structural properties, it has tension, it can be stretched, and it can be compressed.
So it's not just math on a chalkboard.
No, it's intensely physical. In this framework, gravity is no longer just the bending of an abstract grid. Gravity is a physical strain within this elastic medium.
A physical strain.
Exactly. It generates a literal pressure gradient. So when a star is sitting in space, it is physically pulling and straining the medium around it. Much like, a heavy bowling ball stretches the fabric of a trampoline, but obviously in 3 dimensions.
Okay, so if gravity is a physical strain on a physical medium, what happens during the birth of a black hole? Because a stellar collapse isn't just a heavy object sitting there.
No, it's incredibly violent.
Right. It's the fusion engine of a massive star shutting off.
Yeah.
And the crushing weight of all that matter just violently imploding.
And under general relativity, that implosion never actually stops. The matter crushes down into that mathematical point of infinite density, the singularity.
Which always felt a bit like a math error to me, honestly.
A lot of physicists feel that way. And that's the point here. Physical materials, even cosmic fundamental ones, have limits. In the AM framework, as the dying star collapses inward, the strain on the surrounding absolute medium spikes dramatically.
The pressure just builds and builds.
Right, until it hits what the paper defines as a hard, irreversible boundary.
A hard boundary. So that implies a physical stop. It means the collapse hits a wall and cannot go any further.
That is exactly the physical reality AM proposes. Mathematically, this boundary is tracked by a metric called the scalar dissociative pressure.
Okay, scalar dissociative pressure.
We denote it with the Greek letter epsilon. You can think of epsilon as a stress test for the fabric of the universe. It measures how close the absolute medium is to total structural failure.
So in a normal region of space, like out here near Earth, what is epsilon?
It's essentially zero. Around a heavy star, it's higher, but during this violent stellar collapse, the pressure just skyrockets. And when epsilon reaches exactly 1, the system hits absolute saturation.
And the collapse violently halts.
It halts completely.
Let me stop you there because the mechanics of that halt are so crucial. If I have trillions of tons of stellar material rushing inward at like a fraction of the speed of light, and it suddenly hits epsilon equals 1, what physically happens to all that matter?
At the exact moment epsilon reaches 1, the system undergoes a phenomenon called dynamical freeze-out.
Dynamical freeze-out.
To understand this, we have to look at something called relaxation time. In any physical system, if you perturb it, say you poke a water balloon, the water sloshes around until it settles back into equilibrium, right?
Right, the jiggling.
The time it takes to settle is the relaxation time.
So it's the time it takes for the internal parts to interact and dissipate the energy.
Exactly. But at epsilon equals 1, the strain on the medium is so absolute, so saturated, that the relaxation time diverges to infinity.
Wait, infinite relaxation time. So if a particle inside this collapsing star gets bumped, it would take an infinite amount of time for it to pass that energy to the next particle.
Yes, which means internal interaction completely ceases. All internal degrees of freedom drop to absolute zero.
Whoa.
The matter vortices, the actual photons, neutrons, the physical plasma that made up the dying star, they are permanently decayed.
So the star is just gone.
The physical matter is gone, yes. But their kinetic and mass energy doesn't just disappear, though. It is entirely converted into static elastic energy.
Right.
And that energy is permanently locked within the strain of the absolute medium itself.
So instead of an infinitely deep pit with a tiny point of matter at the bottom, like GR says, the black hole is more like a frozen knot in the fabric of space.
That is a brilliant analogy, yes. The paper formally calls this the static dynamic duality principle, or SDDP.
SDDP, got it.
It proves mathematically that a system saturated at epsilon equals 1 has zero internal dynamics. The strain of the massive collapse is locked in place. The energy is massive, but literally nothing is moving.
It's totally static.
This frozen knot of maximum strain is the canonical black hole state in the AM framework.
Okay, I'm picturing a thick rubber band. You wind it up, twisting it tighter and tighter. Eventually you reach a point where the rubber band physically cannot take a single millimeter more of twisting.
Right, it starts to buckle.
Yeah, it is completely saturated with potential energy. It's a state of maximum strain, but there is no kinetic movement. It's just locked.
The rubber band is saturated, exactly. And the matter that did the twisting is gone, completely consumed and converted into the twisted stress of the cosmic fabric itself.
Okay, that makes physical sense to me. It actually resolves the headache of the infinite singularity. But this is where I have to push back hard.
Go for it.
If a black hole is a completely maxed out, saturated knot in the universe, how on earth does it grow? Because we know black holes eat. We've seen them accrete gas, they rip apart stars, they merge with each other. If it's already hit the hard boundary of epsilon equals 1, how can it take on more mass?
And that question takes us right into the second phase of the life cycle, where the destinies of small stellar black holes and the supermassive black holes violently diverge. As you noted, black holes do grow. Their mass increases through accretion. But the absolute medium framework introduces a mechanism called the AM structural density law. And it creates a really profound paradox.
What kind of paradox?
Well, in our everyday experience, if you pack more mass into an object, its density increases, right? Or at least stays the same if it expands proportionally.
Yeah, more stuff usually means denser stuff.
But the structural density law mathematically dictates that as a black hole's mass increases, the density of the absolute medium at its horizon actually drops. It plummets.
Wait, why would it drop? If I'm throwing more stars into this frozen knot, shouldn't it get tighter and denser?
You would think so, but it has to do with how the elastic medium scales to accommodate that new energy. The density is inversely proportional to the cube of the mass.
The cube of the mass, that's a huge drop-off.
It is. Let's ground this in real numbers so you can see the disparity. If a star dies and creates a typical stellar mass black hole, say roughly the mass of our sun, the density of the frozen medium at its horizon is incredibly high.
Like how high?
We are talking about 3 times 10 to the 22nd power kilograms per cubic meter.
That is almost incomprehensible. That's vastly denser than an atomic nucleus.
Exactly. It is a profoundly dense, tightly wound knot. And because that horizon density is so astronomically high, a stellar mass black hole has an abundance of structural support.
The medium is holding it together.
The surrounding medium is gripping it tightly. It is eternally stable. It will sit there as a frozen epsilon equals one state forever.
Forever.
Okay.
But the universe doesn't just have stellar mass black holes. We have the monsters. The supermassive ones anchoring galaxies.
Let's look at Sagittarius A, the supermassive black hole at the center of the Milky Way.
Our own galactic center.
Right. It has a mass of about 4.1 million times that of our sun. According to the structural density law, because the mass is so high, the density at its horizon has scaled down drastically.
Okay, so what's the density of Sagittarius A?
Its density is roughly 440 kilograms per cubic meter.
Wait, let me just process that. 440 kilograms per cubic meter. Liquid water on Earth is about 1,000 kilograms per cubic meter. Are you saying the terrifying gravitational anchor of our entire galaxy is like less dense than the water in my bathtub?
At its horizon boundary, yes. That is exactly what the math says.
That is wild.
And it gets crazier. If we scale up to the true behemoths like a billion solar mass black hole in a distant quasar, the density at its boundary is comparable to a near vacuum. It drops to 10 to the negative 5 kilograms per cubic meter.
So a heavier black hole is actually structurally weaker and fluffier. That feels so counterintuitive.
It does, but it's structurally true.
If I'm understanding this right, it's like trying to build a skyscraper, but the only material you have is meringue.
Meringue, I like that.
Yeah, like if you build a one-story house out of meringue, it might hold this shape. But if you try to build a 100-story skyscraper out of meringue, the sheer mass of the structure is completely at odds with the airy, weak density of the material. The bottom layers are just going to crush outward under the weight.
The meringue skyscraper captures the physical dilemma perfectly. The reason this density drop is absolutely fatal for the black hole lies in something called accessible strain modes.
Accessible strain modes.
Think of these strain modes as the internal steel scaffolding holding the frozen knot together against the inward pressure of the surrounding universe.
Right, okay, the steel beams inside my meringue.
Right. Because the density drops proportionally to the cube of the mass, the number of those accessible strain modes, the steel beams, drastically reduces.
Oh, I see.
As the black hole grows into a supermassive giant, the internal scaffolding practically vanishes. It is trying to maintain this incredibly extreme state of maximum infinite relaxation strain, but it simply lacks the internal density to support that boundary against the outside environment.
So if I keep throwing mass into this supermassive black hole and the density keeps dropping, the meringue skyscraper gets taller, heavier, and structurally weaker, all at the exact same time.
Precisely.
At a certain point, the whole thing has to give way. The structural failure is inevitable.
It is absolutely guaranteed. And that brings us to the trigger point, because we must define the exact mathematical threshold where the skyscraper collapses.
Right, because physicists never make a claim without an equation to back it up. How does Barua's paper calculate the exact moment of failure?
The AM framework introduces a dimensionless number called the support functional. The paper denotes it as a script F with an AM subscript.
So FAM.
Exactly. This functional is essentially a stress test ratio. It calculates the amount of internal scaffolding, those accessible strain modes, versus the external pressure pushing inward from the surrounding cosmic medium.
It's a battle of forces, internal tension holding the boundary outward versus the ambient universe pressing inward.
Exactly. And because the internal scaffolding decreases as the mass increases, the value of the support functional, FAM, goes down as the black hole eats. It's mathematically proportional to 1 over the mass squared.
So it's literally a ticking clock. Every time a supermassive black hole swallows a star, its support functional ticks downward.
Yes. And the critical moment happens when FAM drops below the value of 1.
Less than 1.
Right. When the ratio flips, the external pressure officially overwhelms the internal scaffolding. The moment that threshold is crossed, a massive mechanism is triggered, which the paper calls the terminal identity transition principle.
Terminal identity transition. That sounds apocalyptic. What happens to the black hole?
It means the object, mathematically and physically, can no longer exist as a black hole. When we solve the equations for the moment FAM drops below 1, we get a strict, hard mass cutoff for the universe. We call it MCRIT.
MCRIT. Okay. So supermassive black holes cannot grow infinitely.
They cannot.
What is the universe's weight limit then?
The math places MCRIT roughly between 10 million and 100 million solar masses.
Really? That low?
Yes. If a black hole tries to grow significantly beyond that threshold, the internal pressure fails, the boundary cannot be sustained, and the terminal identity transition begins.
Okay, I need to pause here and emphasize just how massive of a fight you are picking with Einstein right now.
It's a huge fight. Standard general relativity states unequivocally that black holes can eat forever. You can have a black hole that is 10 billion solar masses, 100 billion solar masses, and standard physics says it will just sit there, eternally stable, happily warping geometry until the heat death of the universe.
GR does predict eternal stability, regardless of mass.
But the AM framework is saying no. It's claiming that above this critical threshold, the frozen identity is destroyed, the saturated boundary breaks.
Exactly.
But here's my major problem with this, and I'm channeling the skeptical audience here. Doesn't standard physics have a very strict no-go theorem regarding frozen states?
It does, yes.
Right. If your material is saturated at epsilon equals 1 and all internal dynamics have completely stopped, the rules of thermodynamics and quantum mechanics say you are stuck. You cannot smoothly evolve out of a frozen state. You can't just casually dial the pressure back down from 1 to 0.5.
You really can't.
So how does this supermassive black hole transition into anything else without completely breaking the laws of physics?
You've hit on the exact paradox that makes Baroua's paper so revolutionary. You are absolutely right to bring up the no-go theorem. It mathematically forbids a continuous, smooth path from a saturated state back to a lower strain state, assuming you stay within the same system.
Okay, so the black hole is structurally failing, but the laws of physics say it's not allowed to change its state. It's a true paradox.
It is a paradox, and the way nature escapes this paradox without violating its own laws is through the deep mathematical machinery of functional analysis. The universe forces a transition, but it doesn't do it smoothly.
Walk me through this. How does the universe force a change if a smooth path is forbidden?
We call it the necessity theorem, because the no-go theorem forbids a smooth walk from, say, room A to room B. The system has no choice but to undergo a discrete, violent identity change. The floor of room A essentially gives out, and the system plummets into a completely different mathematical framework.
Like a quantum jump, but scaled up to a supermassive titan.
In a sense, yes, a macroscopic jump. We map this projection using functional analysis. In this branch of mathematics, our frozen knot, the saturated black hole, exists as a singular state in what is called L-infinity space.
L-infinity space, so an infinite space.
Well, it represents a space of functions that are bounded but mathematically singular. It perfectly describes a state with infinite relaxation time, where internal dynamics have ceased. The black hole is trapped in L-infinity.
Okay, stuck in L-infinity.
But here is where the universe intervenes. There is a fundamental rule in the AM framework called the energy space equivalence theorem. It proves that any state of the absolute medium that possesses a finite amount of energy absolutely must belong to a different mathematical space.
What space is that?
It must belong to L2 Hilbert space.
Okay, let me make sure I follow the logic here. The black hole is chilling in L-infinity space because it's a frozen singularity in time. But because it still holds a finite amount of trapped energy, the deeper laws of the universe say, you don't belong here, you belong in L2 space.
Exactly. As long as the internal scaffolding held up, the system could sustain the contradiction. But the moment FAM drops below 1, the support fails. The system cannot maintain its singular state in L infinity anymore.
Right.
The universe forces it to project into L2 Hilbert space via a mathematical function known as a transition operator, denoted as operator T.
Okay, I want to make sure the physical reality of this math is clear. We were talking about a physical phase change, right?
Yes.
I'm thinking about supercooled liquid water. You can take a bottle of ultra-pure water and cool it well below its freezing point, and it stays liquid. It's in a state it really shouldn't be in, just like the black hole trapped in L infinity.
Yep.
It's precarious.
Very precarious.
But the moment you tap the bottle, the moment the internal support fails, the water instantly snaps into ice. It's a violent, irreversible phase change that releases energy and fundamentally changes the identity of the system from liquid to solid.
That is a brilliant physical analogy. The supercooled water snapping into ice perfectly captures the suddenness and the irreversibility of the transition operator T. When operator T is applied, the projection is non-invertible.
Meaning you can't unscramble the egg?
Precisely. Once the transition happens, the exact configuration of the original frozen knot is lost forever. Information is destroyed. But crucially, operator T ensures strict global energy conservation.
So even though the identity changes, the energy ledger remains perfectly balanced.
Yes, the ledger is balanced. The math dictates that the static energy of the original saturated state, let's call it E sub S, must perfectly equal the energy of the newly created state, E sub S prime, plus whatever energy is violently radiated away during the phase change as waves. We call that ERAD.
Okay, so E sub S equals E sub S prime plus ERAD.
Exactly. Energy is perfectly conserved.
So the AM framework introduces a forced structural instability to solve the paradox.
Exactly. Standard physics assumes the state just exists forever. AM proves it is a finite system boundary. And to prove that this snap into a new state doesn't just create a chaotic, universe-destroying explosion, the paper utilizes the Loomer-Phillips theorem.
And what does that theorem guarantee?
In functional analysis, the Loomer-Phillips theorem guarantees that the new system generated by this operator is causally stable and well-posed.
Okay.
It means the universe acts as a safety valve. The massive release of energy doesn't break causality. It strictly governs the dissipation of the object into a finite-dimensional spectral subspace.
Okay, so the meringue skyscraper collapses. The supercooled water snaps into ice. Operator T forces the black hole out of its frozen existence and projects it into a completely new L2 state.
Right.
But what actually is this new state? If it's no longer a black hole, and it's obviously not a star, what is left behind in the dark?
This is where we reach the dissipation phase. The new system, which the paper labels S prime, is utterly distinct from anything predicted by standard general relativity. It does not matter. And it has no event horizon.
Wait, no event horizon? So light can actually escape?
Yes. It is an unfolding, dissipative, elastic strain field.
An unfolding strain field. Let's break that down physically.
Sure. In the new S prime system, the scalar dissociative pressure has finally dropped. Epsilon is now less than 1. Because the pressure is relieved, the dynamical freeze-out ends. Finite degrees of freedom return to the system, and the relaxation time becomes finite again.
Which means the internal dynamics can interact again. Things can move.
Exactly. The immense, pent-up elastic energy that was locked inside the frozen knot is now allowed to unwind. It is governed by a damped wave equation.
Unwinding?
Yes. The static strain is actively converting into propagating waves in the absolute medium.
If there's no event horizon anymore, what does the boundary of this object look like? Is it just fuzzy?
The paper models the boundary as a dissipative layer. The edge where the event horizon used to be becomes a bleeding edge. The saturated strain literally bleeds out into the surrounding universe, unwinding over time. The global energy of the system monotonically decays.
It sounds like a ghost. I mean, it is a literal ghost of a dead black hole.
That's a poetic way to put it, but it's accurate.
The singularity is gone, the trapdoor of the event horizon is gone, but the immense gravitational dent it made in the universe is still there. It makes me think of memory foam.
Memory foam.
Yeah.
Yeah.
If I press my fist into a memory foam mattress as hard as I can, I create a deep well. When I pull my hand away, when the mass is gone, the dent remains, but the elastic memory of the foam slowly pushes back up, gradually recovering its shape and dissipating the strain.
That is an exceptionally accurate way to visualize the S prime phase. It is a macroscopic memory foam dent in the absolute medium. The matter is completely gone, but the elastic memory of the cosmic fabric is slowly radiating its stored energy away as it returns to equilibrium.
Okay, it's a beautiful poetic image for astrophysics. But this brings me to my ultimate challenge for this framework.
The evidence.
Yes. A beautiful mathematical story is ultimately just philosophy, unless it leaves a footprint in reality that we can measure. If these giant billion solar mass black holes are structurally failing and dissolving into memory foam strain fields, where is the proof? You promised me a smoking gun.
And Barua's paper absolutely delivers the smoking gun. This brings us to the final act, the observational signatures. The absolute medium framework doesn't just offer an alternative math trick, it makes highly specific, falsifiable predictions that can be tested right now.
Okay, let's hear them. What is the first piece of evidence?
The first is the observed mass gap in the universe.
The mass gap.
Yes. Astronomers have long struggled to explain why we don't see supermassive black holes that vastly exceed tens of billions of solar masses. If black holes can eat forever, as standard GR claims, we should occasionally find eternally stable black holes that are unimaginably huge. But we don't. There seems to be a hard ceiling.
And the AM framework naturally provides the mechanism for that ceiling.
Yes. The terminal identity transition provides the exact mathematical mass cutoff. They don't exist because they structurally cannot exist.
Okay, a mass cutoff makes logical sense. But what about these dissolving ghosts? Can we detect an unwinding strain field?
We can't see them with traditional optical telescopes because they aren't emitting light, but we can hear them.
Hear them.
Gravitationally speaking, yes. As the S-prime system dissipates, that bleeding edge we talked about emits ultra-low frequency gravitational waves. The paper calculates a characteristic frequency for these waves based on the mass of the original object.
And what frequency range are we talking about here?
For these supermassive giants, the math translates perfectly into frequencies in the nanohertz to microhertz range.
Nanohertz.
Yeah.
Meaning the wave oscillates incredibly slowly. Like a single wave cycle might take years or even decades to pass completely through the Earth.
Exactly. And this is where theoretical physics crashes into observational reality. The specific prediction links perfectly to current stochastic background data from pulsar timing arrays.
Oh, let's take a quick detour to explain pulsar timing arrays, or PTAs, so the listener understands how monumental this is.
Good idea.
Pulsars are the rapidly spinning, incredibly dense cores of dead stars, right? They shoot beams of electromagnetic radiation out of their poles.
Right.
As they spin, those beams sweep past Earth like cosmic lighthouses. And they spin with such staggering, perfect regularity that astrophysicists basically use them as galactic metronomes.
They are some of the most precise clocks in the universe.
So we monitor a massive network of them, an array. If an ocean-sized gravitational wave rolls through our galaxy, it literally stretches and squeezes the fabric of space between Earth and those pulsars.
And when space is stretched or squeezed, the distance the pulsar's light has to travel changes slightly.
Which means the tick-tock of their signals arrives slightly early or slightly late. By watching for these microscopic deviations in our cosmic clocks, we can detect massive, low-frequency ripples of gravity washing over us.
And recently, massive international collaborations like Nanograv and the European Pulsar Timing Array have detected exactly that. They have found a stochastic background. It is a low, continuous hum of nanohertz gravitational waves permeating the entire universe.
The hum of the universe.
Yes. The AM framework predicts that this hum is generated by the dissolving S-prime fields. It predicts that the wave spectrum should have a spectral index, denoted by the Greek letter gamma, of roughly 3 to 5, and that perfectly matches the current PTA results.
But wait, doesn't standard general relativity also have an explanation for this hum? I thought GR claims that this background noise is caused by supermassive black hole binaries like two giant black holes orbiting each other, spiraling inward and churning up spacetime?
It does. Standard GR strongly assumes the hum is caused by orbiting binaries. But here is the definitive smoking gun difference between the two theories.
Okay, I'm listening.
GR predicts that these spiraling binary black holes will stretch and squeeze space in a very specific crisscross pattern. We call it a tensor quadrupole wave. If you map how the pulsars in the sky are affected by a tensor quadrupole wave, the data must follow a very specific mathematical curve known as the Hellings-Downs curve.
So standard physics says if the hum is binary black holes, the data will look exactly like this Hellings-Downs curve.
Exactly. But the absolute medium framework says the hum is not a dance between two black holes, it is a sigh. It is the sound of single, isolated strain fields slowly unwinding. Because of this, AM predicts a completely different kind of wave, a scalar elastic wave.
How does a scalar elastic wave physically differ from the crisscross tensor wave?
Instead of stretching space tall and squeezing it thin, a scalar wave expands and contracts space spherically, kind of like a breathing lung. This produces a vastly different angular correlation across the sky.
Different how?
The paper defines this with a specific equation, but conceptually, if you plot the AM prediction on a graph against the Hellingsdowns curve, the AM curve is noticeably smoother and flatter. It lacks the steep, complex dips of the binary model.
So it looks like a gentle rolling hill compared to a jagged mountain peak.
Precisely. Furthermore, because these are single, isolated fields bleeding out energy rather than two massive objects accelerating as they crash into each other, the timing deviations in the pulsars will be smooth and non-chirping.
Smooth and non-chirping. I want to just sit with this for a moment and emphasize the sheer gravity of this data.
Yeah.
We are talking about the ultimate showdown in modern physics.
We really are.
If the pulsar timing array data, as it gets refined and clarified over the next few years, begins to definitively align with this flatter, smoother curve, if it rejects the Hellingsdowns curve,
then the supermassive binary hypothesis collapses.
and it means you haven't just proven that supermassive black holes die. You have proven that Einstein's geometric grid is fundamentally incomplete. You have proven that spacetime itself is a physical elastic medium.
That is the magnitude of what Sriman Barua has placed on the blackboard. If the observational data holds, it forces a complete paradigm shift. The no-go theorem is respected. Global energy is perfectly conserved. But the concept of the eternal black hole is dead.
Wow.
It is replaced by a dynamic mortal entity that is born from strain, structurally fails when it grows too large, and slowly fades back into the fabric of the universe.
It is absolutely staggering. Let's recap the entire journey to make sure we have captured the full scope of this deep dive. Under the absolute medium framework, a star dies and collapses. It hits the epsilon equals 1 hard boundary, freezing all internal dynamics and becoming a saturated knot of elastic strain.
The canonical black hole state.
And then eats. It grows into a supermassive titan. But as its mass increases, its horizon density plummets. The internal scaffolding holding the knot together gets stretched way too thin.
The structural support functional drops below 1, triggering the terminal identity transition.
Right, because it's structurally failing. But forbidden from smoothly unwinding by the no-go theorem, the universe's functional analysis steps in. Operator T forces a violent, non-invertible projection. The system shatters its frozen state, conserves its energy, and becomes something entirely new.
A dissipative scalar strain field, the S-prime state.
The memory foam dent. And that dent slowly unwinds over eons, bleeding its gravity out into the universe as ultra-low frequency nanohertz waves. A quiet hum that we are just now beginning to detect with our pulsar metronomes.
A mathematically rigorous, thoroughly observable life cycle from fiery collapse to a silent, dissipating whisper.
It is a breathtaking, paradigm-shattering way to look at the night sky. The invincible monsters in the dark actually have a lifespan. But as we wrap up this deep dive, understanding all the mechanics we've just discussed, it leaves me with one final, incredibly provocative thought, a real lingering question.
I'd love to hear it.
We know that supermassive black holes act as the gravitational anchors for the centers of almost every major galaxy we see, including our own Milky Way. The swirling gas, the billions of orbiting stars, the entire complex galactic structure is dancing around the gravitational pull of that central mass.
Right, they are the anchor points.
But if the AM framework is correct, if these supermassive black holes inevitably cross this critical mass threshold, structurally fail, undergo a terminal identity transition, and dissolve into diffuse non-matter strain fields that slowly bleed away their gravity, what happens to the galactic rotation they leave behind?
That is a phenomenal question.
Are we right now living in galaxies that are tethered together not by infinite bottomless pits, but by the fading ghosts of dead singularities?
That is a profound implication. If the central anchor of a galaxy dissolves into an unwinding strain field, the orbital dynamics of billions of stars must inevitably adapt to a mass that is no longer infinitely concentrated, but actively dissipating into the cosmic ocean.
The textbook is completely broken, and the muddy waters of astrophysics are looking deeper and more mysterious than ever. Keep your eyes on the pulsar data, everyone, because the background hum of the universe might just be the greatest ghost story ever told.